Welcome to OP Studio by OpenPhase Solutions. In this quick tutorial, I'll show you how to simulate additive solidification of nickel aluminium using built-in presets. We'll go step by step from setting up the model to running the simulation and visualizing the results without writing any custom code. Once OP Studio starts, you'll see the project selection dialog. For this tutorial, we'll use a predefined workflow, so I'll select Choose Preset. In the preset selection menu, OP Studio provides several predefined simulation templates. For this tutorial, we'll select Additive, which is configured specifically for additive solidification of nickel-aluminum binary alloy. In the phase setup step, the additive preset automatically selects the two elements, nickel and aluminium. It also defines three phases, the liquid phase, gamma phase, and gamma prime phase. We'll keep these unchanged for this simulation and proceed by clicking Apply and Continue. In the left panel, you can see all the modules that are active for the simulation. First, we'll focus on the Runtime control module. Here you can see the total number of time steps is set to 100,000. The simulation output is written to disk as VTK files every 1,000 time steps. And the screen output is also updated every 100 time steps so you can monitor the simulation progress. The time step size is set to 500 nanoseconds, and the simulation is configured to run on 12 OpenMP threads. In the Grid Parameters tab, the grid spacing of 50 nanometers is used, and the simulation domain is defined with a grid size of 51 cells in the X direction and 101 cells in the Z direction. As it is a 2D simulation, 0 cells are selected in the Y direction. Additionally, one boundary cell is applied in each dimension, which is already set by the preset. In the Temperature tab, the initial system temperature is set to 1600 K. A temperature gradient of 10,000 Kelvin per meter is applied in the Z direction. In the Temperature Control tab, linear cooling rate of 1000 Kelvin per second is applied. In the Nucleation tab, nucleation of the gamma phase in liquid and gamma prime phase in liquid is enabled. Additionally, gamma nucleation is allowed at the bottom of the Z direction in the liquid phase, while gamma prime nucleation is allowed at grain boundaries. In the nucleation input mode, nucleation density is selected, with the density value specified here. For more detailed information about any parameter, you can click on the question mark icon next to it. For example, clicking the question mark in front of time step will show a description explaining what the time step represents. Similarly, clicking the question mark next to OpenMP threads provides information about how OpenMP threads are used. After clicking Apply and Continue, the Microstructure tab. For this simulation, no changes are required here, so we'll simply click Apply and Continue again. Finally, click Start Simulation. You'll be prompted to save the preset and select a directory where all simulation output data will be stored. Once confirmed that the simulation starts, and you can monitor the progress through the output displayed in this panel below. If you now open the output directory, you'll find an OPI file where all simulation parameter values are stored. For example, here you can see all the runtime control parameters used for this simulation. The simulation log shows output written every 100 time step. Here we can see that simulation has reached 2200 time steps. To visualize the plots in OP Studio, click on Update Data. Here we select volume fraction, and you can see liquid phase is decreasing with time, while gamma phase, which is represented by the green line, increases. If you select the Temperature tab, you can see that the temperature decreases with time at a rate of 1000 Kelvin per second. To visualize the simulation output, which was saved in the preset folder, open ParaView. From the VTK directory, load the phase field file for this simulation and click Apply. Next, select the phase fields. You can also adjust the phase field color bar if needed. Then, click Play to run the simulation from the initial to the final time step. You can see the liquid phase in red, from which the gamma phase solidifies from the bottom of the Z direction. The red region remaining at the end represents the liquid phase. Now, import the composition files and click Apply, then select the aluminum mole fraction. Here you can see that the aluminum mole fraction is lower in the gamma phase and saturated in the liquid phase. You can also perform a line scan by selecting the line scan option and select the scan range. In this case, we select 5 as the fixed position for the line scan. And along the Z direction, the scan extends from 0 to 100. The line scan results show both the weight fraction and mole fraction of aluminum and nickel. You can deselect the weight fraction to display only the mole fraction in the graph. From the plot, you can see that the aluminum mole fraction increases along the Z direction. And within the liquid region, it reaches its maximum saturated value. Further, you can also visualize the temperature profile. Here you can see the temperature gradient along the Z direction, which was defined in the Temperature Settings tab. You can also visualize the temperature evolution over the entire simulation time by adjusting the temperature range and clicking play. These are the final visualization results of the simulation. If OP Studio fits your workflow, you can download the trial version by visiting our website, OpenPhase Solutions, and clicking Download Free Trial. You can also explore the licensing options by selecting View Plans. Thanks for watching and see you in the next tutorial.